Hello everyone. So today we will be examining Mirai's battle over Internet of Things. Um, so let's get started with the basics as to what Mirai is and what is this Internet of Things. So Mirai is nothing but a malware which takes control over certain network devices and it converts these network devices into botnets, which are further used to perform large-scale network attacks like DDoS. Internet of Things is just a connection of certain types of devices which usually have sensors, software, and other technologies which are used to uh, establish connection with each other, exchange data, and so on. So, what does Mirai want? So, Mirai's purpose is to infect as many IoT devices as possible and use these compromised devices to launch a much larger network attacks. So, what is a botnet? I've mentioned botnet earlier. So, it's nothing but a network of all these hijacked computers which are used to perform attacks like DDoS and so on. So, Mirai converts vulnerable devices into botnets. Now, just an overview of how Mirai works. So, first of all, it has to gain access to a vulnerable device. It does that by exploiting system vulnerabilities like unchanged passwords and so on. Once it gains access to a device, the next thing that Mirai wants to do is to find out what other vulnerable devices are present in the network, and therefore it works like a worm in order to scan for all these vulnerable devices. Now, how will it find for who vulnerable devices, whom will it establish connection with? In order to do that, it will create a large number of randomly assigned IP addresses. So it will create these random destination IP addresses to which it will just send out packets and it will try to brute force to log into the system. And in order to create these random numbers, it uses an algorithm which is called as a random number generator. So this is the ecosystem. So this is the network of all the compromised IoT devices. So these were earlier vulnerable, not infected, but now Mirai has gained access to these devices and hence they are called compromised IoT devices. Mirai's ecosystem has a loader which bootstraps all these compromised devices. Bootstrapping means it will install some programs, it will open some ports, it will block some ports, and all those things which are required for Mirai to function, all that bootstrapping will be done. The second is it will create connection with the CNC server. CNC is nothing but command and control server. So these compromised devices, they send data to CNC server. The CNC server analyzes all this report and it's in turn sends the list of commands that need to be executed on the devices. So this is the ecosystem. Now, what there are certain characteristics of Mirai which distinguishes it from other malwares. So some of them include that once Mirai gains access over the device, it just blocks off the entry point in order to gain exclusivity. It immediately, once it gains access, it immediately starts scanning for other vulnerable devices. It uses the RNG to create a target audience, and we've seen that it usually uses telnet port 23 and it tries to brute force to log in into the systems using a built-in credential list. It then creates a connection with the CNC server we saw in the previous slide, and these connection details, they are all hard-coded, and even the list of commands that it receives. So all that certain things are hard-coded in the source code itself. All right, now here are some of the implementation details. So if Mirai fails to bind to port to 23 because some other process is using it, so here port 23 is nothing but your telnet port. It kills all other telnet processes so that it can bind to this port. Then once it does that, once it establishes a connection, it will fork off a separate process to scan for other vulnerable devices. Now what all things, so once it has decided that it has to send out packets. That is, it has to establish connections with many devices to find out vulnerable devices. There are certain things it will have to inject in IP and TCP headers. So, what is What is that information? So three things are injected into these packets. One is a random source port which lies in this range. Second is a random destination IP to which it will send these packets. And the third is the random IP ID. These packets are then sent to all these random destination IP addresses. Now, one of the important details in creating these random values is the RNG algorithm, and its RNG algorithm follows something called as linear shift feedback register design. Because of this, if you have a random number, then we can predict the previous random numbers and even the next random numbers. This is because the next random number will directly depend on the last random number generated and the one that was the 3 iterations ago. So this is an important flaw which we can exploit to detect and prevent Mirai. All right. So we are following this paper where this paper thoroughly understands how Mirai works and how its variants emerged and how they compete with each other, how the battle ensues, and so on. So this paper it uses three main things to analyze the Mirai botnet thoroughly. First is the network telescope. Second is the honeypots. There were about 7,500 honeypots, and then you have the operator net flows which I used to study the behavior. That is, how does Mirai establish connections? How does it propagate? Uh, uh, how are the reinfections occurred? And all those things are studied under operator net flows. So let's take a look at them one by one. So the only purpose of network telescope is how does Mirai find out about all these vulnerable devices in an ocean of billions of IoT devices out there? How can it find vulnerable devices? In order to study that, this paper and the researchers they have used something called as a network telescope. So all these devices that were infected could be identified because of certain indicators. And some of them include these TCP packets that were modified because, as we've seen, that TCP IP packets are modified because some of the values are the random values are inserted that were generated using the RNG algorithm. Also, on startup Mira instances, they pick random values for the window size, which is not common, and the source port till the infection is there. So that is how we can identify the infected devices. For honeypots, they are nothing but very lucrative devices whose purpose is to attract malwares in order to study them. So here we see that the user agent it listens on port TCP 23 because Mirai usually attacks on the telnet port 23, and whatever traffic is happening on that port it is all tunneled to a virtualized environment which where they are studied. As a result of analysis of these honeypot systems, the researchers they came up with certain statistics. That is, about 300 million login attempts are received from about 2 lakh unique sources. Brute force attacks are attempted in order to log in. They could also obtain a hard coded list, that is username password list that was used for the brute force login attempts, and the entire list was obtained because the nature of the Mirai is such that it doesn't stop after a successful login. It will keep on trying the entire list. Then there was certain list of commands that Mirai runs, and the last command is known to be bin BusyBox Mirai. Now, if the device is vulnerable, if the connection was successful, we would get a response from BusyBox as Mirai Apple not found. If it's a non-vulnerable device, it would simply throw out an error. Now, some of the variants even modified the malware such that they could gain access to the working shell of the infected device. Now comes the net flow. So it's basically to understand support infrastructure. Once the device is infected, how does it behave? Because different variants grow in different regions. Why is that so? All that analysis is done using net flows. And in order to maintain privacy of the users, the source and destination IP addresses were masked. Further breakdown, we have seen that Mirai depends on the randomness RNG algorithm, and it injects these random values into the packets. Now, we have also seen how RNG algorithms, one major characteristic makes it predictable and deterministic and periodic in nature. Now, the way PRNG, that is your algorithm to create these random values, is that a seed is fed to get a random output of streams. Thus, if we get access to a Mirai packet, if we get these random values, we can attack this seed, find out its value, and hence we can predict what the other next random value could be. And then, even before the device gets infected, we can predict that this particular device may be infected by Mirai. That is one of the major flaws of Mirai, and this happens because PRNG, it's a computer, it's an algorithm, and therefore it will generate predictable data. All right, so now Mirai, we've seen it injects certain things into packets. It modifies the four fields. It modifies epoch time, process ID, the parent process ID, number of clock ticks, and therefore it could create an entropy, a randomness of 94 bits. But due to these implementation flaws, effective entropy is only 32 bits, which makes Mirai easy to detect. Now, what makes Mirai detectable? We have seen some of those things, right? So the RNG, the finding, attacking the seed, all these things makes it detectable. Other thing is that the connection that is established with CNC is done over plain text, and the address and the port is hard coded in the source. Also, the commands that are given by CNC, they have a binary status code, and therefore they can be easily analyzed. We have seen characteristics of Mirai which distinguishes it from others. Mirai usually works with TCP port 23. Its source port usually lies in this range. And we have seen that it has entropy of 32 bits, which makes it very easy to get detected. So why was Mirai so detrimental? It is because Mirai was mutating. You could easily modify Mirai. The Mirai source code was open source, so this led to the birth of many, many variants, and then later each of them competed with each other, which we will see later. And some of the variants includes Miori, Daddy, L332, Akuma, Hajime, Josho, Masuta, etc. And following is the graph of their market share in the year of 2018. And at that point in time, we see that Mirai and Miori were some of the variants that dominated the market. Now, once these variants increased, right, and the number of IoT devices in the network were there. So now each of the variant competed with each other in order to gain access to as many IoT devices as possible. And thus there was a battle that ensued between all these variants. So here we see that the um, now, in order to gain access and in order to block others, what the generic technique used by most of the variants is that once it gains access, it immediately cuts off the process. That is, it shuts down telnet SSH so that other variants can't infect it. Also, there is something called as reinfection. That is, once the system, all these variants, they are not self-sustaining. Once you reboot the system, it becomes vulnerable again, and this time between the reboot and reinfection is where the competition happens. So this behavior is usually called as takeover behavior. So in the below graph, we see that there is certain overlap between the variants. So this is when one variant took over the other in the time frame, between the reboot and the reinfection. Now, some variants they try to reinfect the same device after the reboot by using the CNC server because now they already know the successful login credentials, so they just try to use that single thing to reinfect it again. A second is alive pings are sent to CNC to monitor the state of the device, and this preempts other botnets, other variants from taking control over the device. This is how each of the variants they compete with each other. One important factor in this competition is the size of the botnet because larger the size, greater number of devices can be scanned, greater number of devices can then be gained control over, and therefore larger botnets have an upper hand. Now, for smaller botnets, in order to compete with these larger botnets, they customize certain properties. They change their variants in order to gain as much control as possible. Also, in this battle, then arises a situation which is called as concurrent infections, which means that a single device is infected by two or more Mirai variants. Why does this happen? This happens because Mirai usually runs on the processes 23, 22, 80 and cuts them off. Okay. However, certain devices they don't run their telnet on the defined default ports, but they run them on 2323. Thus, even if one Mirai infects a device, other telnet processes they are still running on different ports not known to Mirai, which is leveraged by other malwares, and therefore a single device can be infected by more than two variants, which is called as concurrent infections. So the following graph shows an example where we see that these two particular variants they are concurrent. However, we also see certain rivals like Masuta and Sora. They do not coexist. Therefore, they have done an excellent job in locking out their competitors and maintaining control over infected devices by themselves. All right. So infections by a variant also depends on geographical locations. So we have seen that large botnets they have an upper hand. Therefore, these smaller players they optimize themselves so that they can gain access to a fair share of IoT devices. And one of those criterias is the targeting devices belonging only to particular autonomous systems. They can target devices that are not mainstream and possibly thus they would not be attacked by the larger players, so they can gain access over them. Also, these variants, the smaller variants, they learn from each other in order to build a strong credential list. The following graph shows how these different variants adopt and how they share passwords. From this graph, we draw certain conclusions that Mirai does not introduce new credentials because if you see here from the graph, there's not much overlap. Therefore, it keeps things to itself. Larger bots only feed from other larger bots and they don't adopt passwords from smaller botnets. However, smaller botnets like Matos, MM, and so on, if you see, they have much larger strain here, which means that they pick up credentials from one another and create and build their credential lists from each other. Now, once you use these credentials, you log in into the system. The botnet sends these credentials to the server, which is responsible for infecting new devices. So this makes customizing infections easier if new devices are discovered. Now, certain responsibilities like these, they are dedicated to a centralized server. Now, why is this done? Because once it is centralized, it is easier to dissipate uh, software updates and the number of instructions to be run, all that is made easier. This centralized server is nothing but loading infrastructure. So once you have successful attempt, a login attempt, okay, I know what the username password is. Therefore, I will not brute force thousands and thousands of credentials. I will just use that known credential to log in. That information comes from the loading server. It's easy to identify a loading server login because a normal malware would take many attempts to log in, but loading server will only take at most a few logins to attempt. So that's how we can easily spot these loading infrastructures. Now in this graph, it shows how different malware strains of Mirai, how the different variants they leverage loading infrastructure. So we see that these circles, they represent the loading infrastructure. We see that the ones in the purple is this variant and the green one is Akuma. So they perform large number of brute force attacks in order to find credentials. Now, because of this nature of the variants, they are vulnerable to blacklisting. That is, certain IP addresses are blocked. Now, in order to mitigate this, because loading infrastructure is faster, it's more efficient, I don't want my loading server to be blocked. So what these bot masters do is that in order to stay undetected, they regularly change their loading infrastructure, or they uh, just cycle them around. So there are a bunch of loading servers, and periodically they just keep cycling around those loading infrastructures to not get detected. So also to avoid detection, some of the variants, what they do is they leverage exclusion of certain IP ranges, because certain IP ranges they belong to enterprise network, government, defense, portal services. So all these important IP ranges they have security mechanisms in place which makes Mirai and other variants detectable. So malwares usually avoid these IP ranges. And this behavior, the researchers could verify by using a technique called as honeypot evasion. And this is the graph which shows that how variants skip over certain IP addresses. So we observe that Mirai, Miori, and Josho, they don't perform any exclusion and they scan for all vulnerable devices, making it easy to get detected. However, other variants like Ovari, they exclude the enterprise range entirely. Cloud variants are attractive across all variants. So these are some of the findings from um, the behavior of Mirai botnets. So this all these points are used against each other. Each variant competes over each other in this battle to gain as much market share to infect as many IoT devices as possible. So that is the ongoing battle. Now let's go back a little bit and see how we can identify the seed. Just a brief recap. A seed is an input to the PRNG algorithm which generates some random output. Now, how can we identify the seed from all these characteristics that we have seen of different Mirai and its variants? So the feature of blocking of IP addresses by variants can be used to obtain the seed used for the attack. So since it is seen that Mirai skips an IP address from its blacklist as a result of blocking of IP addresses, and therefore the state of the RNG is advanced, and RNG is already predictable and deterministic. So combining these two um, conditions, we can identify the seed. We can also brute force the seed and verify if we can reproduce certain sequence of probing packets. So that is another way of identifying the seed. Now it is found that certain variants like these, they adopt customized blacklists, whereas other variants, they run with original Mirai algorithm. Now we have seen why Mirai is detrimental, how can it be detected, but what is the mitigation against it? They can be something as simple as always having antivirus softwares on IoT devices. It can be as simple as changing default passwords and performing sanity checks frequently. Changing default ports, we know that it uses telnet, so we can work on those things to change those default numbers and standard communication with other devices. We could use other mechanisms and not use telnet at all. Other thing is reboot the system periodically, because we know that all these malware strains, they are not self-sustaining. So coming to the last conclusion slide, I'll just conclude it briefly. So the availability of Mirai's source code led to the emergence of many variants, which resulted with, and this, as a result of this, a battle ensued between all these different variants to gain maximum market share. And in order to gain maximum market share, many variants customize themselves. They use techniques like honeypot evasion, blocking certain ports, establishing connection, modification to loading infrastructure, injecting packets, monitoring other variants, building their credential lists, and so on. Misconfigured IoT devices and devices having default passwords, devices without any anti-malware protection are the most vulnerable for infection. And one of the major flaw that makes Mirai detectable is the use of its RNG algorithm, which can be exploited to gain insight into what was exact time of infection, how it proliferates, how it behaves, and so on. And also, we've seen that the success of the botnet, it depends on the installation size, their capability to find vulnerabilities in infected devices, and averting detection. All these three things are used to fight against each other in the battle to gain to gain control over as many IoT devices as possible out there in the market. So that's all from the paper that we conclude on examining Mirai's behavior and mm, the battle among all its variants. And here are some of the references that I used for this presentation. That is all. Thank you very much.